Okay, problems 11 through 15 in Lab 1. We're going to look at something different. We're going to look at where these things fundamentally come from. I just gave you the equations for the error for MGH when you got M and H, but I want to start equipping you to do things when there's more than that, when you've got other equations where you've got to actually determine what the error is. So in the algebra-based class, I'm going to be giving them these error calculations all the time, and they'll just be able to plug and chug. But in your class, you're the winners. You get to actually calculate how it's going to work out in the end. So let's press forward with that. So here, if we have a function of two variables, x and y, so f of x and y, and we're looking for the standard error sigma f on that function. Well, sigma f squared, it's usually easier to work with squares because then we, quite frankly, we just don't have to bother typing the square root over all of this. It's kind of easier to read. So sigma f squared, you've got partial f with respect to x squared, and there's a magnitude here in case it's a complex function. Just, yeah, there you go. Sigma x squared plus partial f with respect to y squared, sigma y squared, so you have the error on x times a partial with respect to f, a partial of f with respect to x, all of both of those squared. The same thing for y. Out here is the third term. In this third term, we are typically going to just say it's 0, but we're going to say sigma xy squared is 0, i.e. the error on x and the error on y are completely unrelated. Now, we came up with a really bogus example of the length of the ruler and length of the spring. Let me give you an example that's probably a little bit better of where errors would be correlated. All right, so let's say I have a beaker. Oh, let me redraw that back on the screen. Okay. Let's say I have a beaker. All right. Oh, it's a great beaker. I'm glad you let me. Oh man, I love that beaker. I'm gonna have to try this again one last time. Sorry about this. I'm trying to learn use a new tool. All right, so I've got a beaker, and this beaker is sitting on a scale. So I'm going to measure its mass, right? And I'm going to look at the height of the liquid in the beaker, and I'm going to measure the height. Oh, I'm off a bit there. I'm going to measure the height. Well, I've got an error on my height, and I've got an error on my mass. Now here's an issue. The central value of the mass moves with the error on my height, doesn't it? Because if I go up, I've got more mass. If I go down, I've got less mass. And if I'm trying to measure the density of this fluid, then I'm potentially introducing a correlation between the mass and the height, because the mass in this instance is in fact a function of the height. All right. So that's something we won't worry about in this class. So almost all the time, unless for some reason we run into something weird and I tell you to do otherwise, this term out here is 0. Okay, so let's take a look at this. We want to look at the standard error on the expected period t of a mass on a spring. So t is 2 pi squared to m over k. We've got an error on the mass. We have an error on the spring constant k. All right, and so what do we have to do? We have to take the partial with respect to f. All right, have partial with respect to partial of t with respect to m. We have to take the partial of t with respect to k. And when you look at doing that, you just have to remember t. Oh, turn this back on. T is 2 pi m to the 1/2 over k to the 1/2. And That doesn't look like anything at all. Man. One last time. T. All right, I may have to give up on this tool. All right, so the way to think about it is T is 2 pi. All right, and so you got square root of m over k. Well, that's m to the 1/2 over k to the 1/2. And if you think about it that way, it's a little easier to take the partial with respect to m and then take the partial with respect to k. Right? So you're going to take the partial with respect to m, square that, multiply by sigma m squared. You're going to take the partial with respect to k, square that, multiply by sigma k squared. And then you're going to have to take the square root of it all, right? Square root of it all to get rid of that 2 right there. Okay. Too bad we are not in class where you can't ask questions, but at least you'll have this to go on and we can discuss it later. All right, problem 12, y equals sine of theta. Theta is this value, it's got a partial error, an error of 1.8 degrees, so we got to take the partial of the sine with respect to theta. Well, derivative of the sine is the cosine, so that's going to give us cosine squared theta times sigma theta squared, take the square root. So in this case, it's just going to end up being y equals cosine theta times sigma theta. Pretty cool. Okay, measurement temperature is stated 1.58%. What is the standard error measurement of temperature difference, T1 and T2? So we've got delta T equals T2 minus T1. Well, delta T, you take partial with respect to T, all right, you're going to get partial. Let's see if I can do this. We will try one more time. Partial T, or, well, okay, I'm writing fine, but what I'm writing is nonsense. Okay. Partial delta T over T with respect to partial T. Right, there we go. Is 1. Right? Equals 1. Partial delta T with respect to, I should really write this as T1 with respect to partial T2, that's a 2 down there, is again 1. All right? So it's 1 in both cases. So what does that give you for the error on this? If you can read all this crayon I have here. Well, that means sigma delta T, right? Sigma delta T is going to be square root sigma T squared plus sigma T. Oh. All right, plus sigma T squared. Right? It's not simply sigma T because we're taking this difference. Why is that? Well, one temperature could fluctuate up, all the other fluctuates down, or they could fluctuate towards each other. There's a broader spread on delta T than there is on either temperature. All right. What is the standard error on a measurement of y if y equals e to the x? Well, partial y, partial x is e to the x. So you're just going to multiply e to the x times sigma x. And this makes complete sense. As you go out in an exponential function, the small variance in x starts creating a larger and larger variance in y. So the error on y grows exponentially. Last one, standard error on x, y, z. So you're going to take the partial with respect to x, multiplied by sigma squared times sigma x squared. You're going to take the partial with respect to y, multiply square that, multiply by sigma y squared. You're going to take the partial with respect to z, square that, multiply by sigma z squared. You're going to take the square root of all that to get the error on w. All right? Any questions at this point? Just send me a note, and hopefully you guys will be able to work through this without much problem. I'll see you as soon as the weather gets better.